I'm going to go through, and even though before we derived the equation for a charging capacitor, I'm going to now derive for a discharging capacitor. You can either watch this, work through it, whatever you want to do, or just pay attention and look at it later. Doesn't matter to me. So if we start with a charged capacitor of a capacitance C, and let's say it has an initial voltage of V0. And then it goes through a resistor of R. Well, using Kirchhoff's rules, which say the sum of all of the voltages around a closed loop equals 0, if this is the negative, positive, negative, then that would give us the voltage across the capacitor minus the voltage across the resistor equals 0. Simple enough. Well, let's write down a couple more of our equations here just to make sure that we don't miss something. Our basic capacitor equation, C equals Q over V. And remember that that's the constant, right? If you double the voltage, you double the charge, but the capacitor's a device. It's like a resistor. You don't double the resistance because you put more voltage across it, which gives us these equations. It gives us that Q equals CV and V equals Q over C. And we're going to use those a bunch. The other one that we're going to use is that I equals, everybody? dQ over dt, yes? Mm-hmm. That one's going to be a little goofy all of a sudden. And I think a little bit, honestly, some of this is a little bit of a, nothing underneath the sleeves, but I need to get to a certain point so I make the math do where I want it to do, okay? And so at this point, when I put in V of the capacitor, right? So that's going to be Q on the capacitor over C minus IR equals 0. And that I is going to be dQ dt. Now, here's where you all know that we're going to get this e to the minus t over rc, right? That's going to be where we finally get to. I bring this over to the other side, I'm going to have a positive r instead of a negative. So this is how they deal with that. They say the dq dt in this instance, since that's a change of charge on the capacitor, isn't the final charge on the capacitor less than the initial charge? It's decreasing. So we're going to say it's a negative change of current. So we're going to say that this is actually a negative since Q final is less than Q initial. Now again, is that a little bit of magic? Yeah, that's a little bit of, oh crap, what did you just do there, okay? But it gets the math where we want it to be. So that's going to give us this, Q over C plus R dQ over dt equals 0. The next thing we have to do is separate so we can integrate, and this is actually a pretty easy one. So we're going to bring that to the other side, giving us the negative that we need. Remember how we always bring the constants to this side? You start getting used to that. And so we get dt over rc, yeah, and there's the negative, and you're like, we got what we need, equals dq over q. So now I'm going to integrate both sides, take out my constants. Sorry, dt equals the integral of dq over q. Now, this one is going to give me t. It actually gives me delta t, okay? But I had someone say, where's the constant, Mr. Murray, on that side? We can deal with it this way if we had to. Again, when you finally get there in calculus, this will make more sense. But if we call this 1 over RC t plus a constant, and I'm going to call it constant 1. Then over here, doesn't this give me log of q? Natural log of q, sorry, plus another constant. Let's call it constant 2. Well, let's take this constant and put it over into that constant, subtraction, addition, and it doesn't really matter. So now I get t over rc equals the log of q plus some other constant. I'm going to call it constant 3 because that's not this c, is it? See what I'm saying? That's a different c. That's capacitance. That's some arbitrary constant so that we can find our y-intercept. Well, let's find that value. So if we take this and we put in our initial values, well, at our initial value is Q naught at t equals 0. So in other words, some initial charge, right? So at t equals 0, we get the log of Q naught plus C. So C3 equals negative log of Q naught. We go over here and we put that in, and we get negative T over RC equals the log of Q minus the log of Q naught, which is, of course, our logarithm rules gives us Q over Q naught. And how do we get rid of the natural log? We take it to the E. This all looks familiar now, doesn't it? Mm-hmm. So now we get E to the minus T over RC equals Q over Q naught, and we get our final equation that Q at some time T will equal Q naught E to the minus T over RC. That's one of our big equations right there. But we ain't done. Let's move on. Well, it turns out, look back again, you see how Q equals CV? Mm-hmm. So over here we're going to have CV at any given time is going to be C, which is still just a constant. And since it's the same C on both sides, we get our voltage, which looks exactly like our charge, which, remember way back when we started on inductors and we said that we found the graphs, and we said Q will always be a maximum when V is a maximum. Same idea. Mm-hmm. Now to get the current. This one we have to be a little careful. We could just kind of do something simple here. If this red doesn't work, just let me know and I'll switch back. So is that dark enough? No, that is not dark enough. We're not going to use that.
I mean, I can see it.
Yeah, I want dark. I like it dark. Whoa, that's a brand new pen that's never going to get used again. All right, we're going back to black. Black is good. Back in black. So we go down here and we know that I equals dq dt. So the correct way of doing this is to take the time derivative of that. It's actually not that bad. Equals. That comes out, and you hopefully remember that d du of e to the u is e to the u du. Chain rule, right? Mm-hmm. Well, it's going to be e to the u, and the integral, or the derivative of that, is going to be negative t over rc, which we're going to multiply through here, and we get I will equal.
Mr. Murray, there's no t.
Sorry, right, because I just took that derivative. Thank you. So this is going to be over RC, and there's this negative, which we're going to deal with in a bit, times e to the minus t over RC. And what is Q over C? Q over C is volts, and volts over resistance is just current. So I equals I naught e to the minus t over RC, and hopefully you're kind of clamoring saying, but there was a negative in there. And they just kind of do this damn thing again where they said, remember that it's actually a negative because it's losing current. That's again a little bit on one of those, like, just the magic, we need the numbers to work out. But this is what we actually find out, okay? And I guess the difference would be the current going onto the capacitor, and you make it negative current going onto the capacitor, okay? Which again, if you were to use a multimeter, can't you see that? You can see the current going on, current coming off. But that's the magnitude of it. And beautifully enough, they're all the same shape, aren't they? Okay? Let's remind ourselves of these shapes. This would be e to the x, would be that. E to the minus 1 would be that. And 1 minus e to the minus 1 would be that going to a value.
E to the minus 1, just a value then.
1 minus e to the 1, sorry, that.
No, like
e
what
to
he's
the
saying
negative
is
1
that you
just a
put e
value.
to the negative 1 instead of e to the negative x.
Oh yeah, to the x, sorry. Yeah. Okay, good job. Okay, we all good? Mm-hmm. All right, so now we have our 3 equations. Okay, let me erase this junk here. And we need all of these basic values. I don't need this either. I want to leave those basic equations up. I'm gonna leave these basic equations as well, because that'll be instructive. So if we take, again, the same equation, the same that we had before, and let's just call this 6 microfarads, and let's call this 2 kiloohms. Kilo meaning times 1,000, okay? Well, we need to pick a voltage. We don't have an EMF here anywhere, so it'd be like, what's the final voltage of the capacitor? What'd you have it hooked up to? And let's just pick a 12-volt battery. Okay, so its initial voltage is 12 volts. Okay, well, let's look down there and let's figure out all of these things. So V naught will equal what? 12 volts. That's our initial charge. Our final charge will be, of course, 0. Our initial current will be 12 volts divided by 2 kiloohms, which will equal, is that 6? 1, 2, 3 will be 6.006. Is that right, Luca?
Yeah, 6 milliamps.
Amps or 6 milliamps. We good on that? Yes? All right. And we need Q naught. Well, Q naught equals C times V, which would be 6 microfarads times 12 volts, which equals 72 microcoulombs. We all good so far? And there's one other thing in all of those equations, which is RC, which is known as the time constant. RC is also oftentimes called tau, and that will equal R, which is 2 kiloohms, times 6 microfarads. That's times 10 to the 3. That's times 10 to the minus 6. So that's going to give me 12 times 10 to the minus 3. Or it's going to equal 12 milli. Notice I didn't finish my sentence there. We need to go back here and learn some basic math. The units of any power must equal
Joules per second.
nothing.
Oh.
This argument must all, just like sine and cosine have whatever's inside that argument has the units of nothing. You say, but it has radians or degrees, which is actually not a unit. If you multiply 30 degrees times this length, you just get that length, you just get meters. There's no such thing as, that doesn't make any sense. I don't even think why I said that, right? So again, the only degrees that matter are kelvins. Kelvins is actually a degrees, right? But degrees as for an angle or something, that actually doesn't do anything, okay?
I know that either radians or degrees are actually units. I think radians are units.
Yeah, but they disappear inside the parentheses.
I know
Because like if you do this, watch. You do the cosine of theta, right, which is in radians. But cosine omega t, that has to be basically nothing. I guess it's radians also. It basically has to be nothing. Okay? This has to have the units of nothing. Okay? Are you saying that that has to be either degrees or radians?
if you're like taking the derivative, it needs to be in radians.
Okay.
Because just because of unit math.
But this has to have the units of nothing. Okay, so if that's seconds, what do those two have to equal?
Seconds.
Seconds. So this is actually 12 milliseconds. And by the way, proving that RC equals seconds, that is not a simple thing. You should sit down and do that. Maybe we'll do that sometime in class. That's a pretty good trick. That takes you a while to figure out. I know it took me 3 or 4 minutes to figure out how RC equals seconds. Now, let's talk about RC again, the time constant. He's actually a good friend of Doctor Who, but he's a time lord. This is a time constant. Not totally different, but kind of. Anyway, that was dumb. So if this time constant again, in 12 milliseconds, what will happen? It will go from full charge to
Discharge.
37% of what's left. It's actually 36.8%. Okay? So this is how long time for 37% of final value. And then 2t will equal 37% times 37% of final value, etc. Right?
Mm-hmm.
Now it's actually 36.8, but you get really close with the 37%. okay? All right, so now let's calculate some of this stuff. Well, we've got a whole bunch of things here, okay? So if we wanted to know, say, well, look, 12 milliseconds, right? That's 37%. How long would it take for you to get half? Well, it's going to be less than 12 milliseconds, wouldn't it? So that gives us something that we know if we got, oh, it took 20 milliseconds, we know we're wrong. So let's find out what time it takes to get to half our voltage.
Would it be more than 12?
No, this goes down to 37%. Like here's 100, it goes down to 37%.
Oh, goes
So
down.
half will be faster in less time. Okay? So let's say our voltage equals 6 volts. There's our voltage equation. It's going to equal 12 volts times E some time over R RC. And I'm just going to put RC because we're going to have to do some algebraic manipulation anyway. And so, you know, actually, let's just do this. Let's just do this just pure algebra. Pure algebra. So,
Pure.
pure. Let's solve for T.
Get rid of those kids.
Yeah?
You log it.
Ooh.
Ooh.
And at that point, I don't care anymore. Because this is easy, yes?
Multiply it.
Okay? So T is going to equal negative RC log of V over V naught. Which in our case, this is 12 milliseconds. And then times the natural log of 1/2, which would give us our value. Which is
8.31 milliseconds.
8.31, right?
8.32.
Whatever.
Truncate, don't round.
Good enough. You see it? You see what happened there? So that was faster, wasn't it? It got to half of it faster than it took to get to 37%. What I'd like for you to get to is to where you can see this and say, oh, I know what the time constant is. That makes sense. Because that number says when it's going to get down to 37% of what's left. And so half of what's left is going to take less time. We good on that? Okay. Energy of the capacitor. That's another value when you do. Let's get rid of this. And just going to get rid of this too since it was already on there. So what about energy? Well, if you look up there, the energy of a capacitor equals 1/2 QV. What are my units here? Coulombs and joules per coulombs, which just gives me joules. But you might say, you know, we've been using this 1/2. Why? Where is that 1/2? So I'm going to need all of this row. Okay, so let's imagine we have a parallel plate capacitor. Here's the positive plate. Here's the negative plate, connected to a battery of some voltage V, or EMF, whatever you want to call it. And it's going to push a little dq. What is dq again? That's an infinitely small charge. You know, when we were doing electrostatics, we just called it Q, but we're going to need a dq because we're going to do calculus. Okay? So we have this little dq that's going to go on. This already has a potential difference of V. This is going to be our final voltage, whatever you want to call it. I guess maybe final. And let's just say this is the V right now as it's charging. Okay? Just to make sure I don't make any dumb mistakes here. So if du, if U in units are coulombs times volts, right? Which would be Q times V, right? Well, then du is going to equal Q times dV.
Q constant.
Well, just stay with me. How I get to that exact thing is a little goofy. Okay, or you could have said that C equals Q over V. That's a constant, right?
Yeah.
Mm-hmm.
Which would then equal dq dV. Yes?
See.
Okay. And so then we solve here, and I'm going to change it to the little q now, equals C dV.
Just regular Q.
What, this one right here?
Yes.
I think this will be easier for you, so let's solve for this, say for this one, right? So if I take this and I substitute that in, right? So now I get, I'm gonna change this to du equals. This goes into there, and so we're gonna have q times dq over c, yes? Okay, and, okay, got that right. Okay, so now, and let's just make those so that they're still the same q, right? So this is q and a little bitty q. Okay, so now we're going to actually do the derivative now, or the antiderivative. Du is going to be 1 over c, because that's a constant, right? The integral of q dq. And I'm going to integrate this from 0 to some final q, and this is going to give me the change of current from some 0 value to u, which is going to equal 1 over c, q, raise it to the power and divide, which gives me 1/2 q over c,
It's q squared.
q squared, sorry, over c, which equals 1/2 q over c times q. So U for a capacitor equals 1/2 QV. Okay, so we're going to write this over here in different color. So we get that the U for a capacitor equals 1/2 QV. Now, what you may or may not know, or I may not have told you, I don't remember, the work done by a battery actually equals QV. And now there should be a great cry should come up from the people that says,
No, we lost some energy.
we lost half of it. Where did we lose that?
Resistance in the wire.
Resistance in the wire. Yeah, let's just imagine you use perfect wires. They are superconductors. Then where else do we have resistance?
Inside the
Battery.
battery.
Inside the battery. The battery itself has an internal resistance, doesn't it? Yes? Do we agree with that?
C.
So, what we are claiming, here's our claim. Our claim is that half of this energy is lost to resistance, which we call joule heating. Okay, we're all good with that, right? And powers work over time.
Yes.
All right? Well, we take this I and we put in what we had before, where I for a capacitor equals I naught e to the minus t over RC. You remember that? And we're going to put that in. So now we get dW over dt equals I squared, which is going to be I naught squared times e to the minus 2t over RC and times R. Now at this point, the book goes ahead and it takes these two. Okay, let's go ahead and deal with those two. And we get I squared, sorry. And again, I know that that's just power, right? But you're going to get I, which is going to be V squared over R squared times R, which is going to equal V squared over R. Yes?
C.
Everybody follow what I did there? Right? Because this is I squared, and this is times R.
Okay.
Right? I squared times R. Okay, so
But
now,
make it- you need the knot though, don't you? Okay.
oh yeah, this is at some rough time t. Sorry, this is at some time t. I think that's the way that works out. I would have to take too long to worry about that. I'm sure if I put this on YouTube, someone will troll me and have to say, well, you're an idiot, it's blah, 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 because you're so smart. Okay, that's why you're watching YouTube. Okay. Anyway, so that this becomes v squared over r e to the minus 2t over RC, I'm gonna multiply by the dt to the other side so we can do an integral. So now, we're gonna get dw, the integral on that side. Can I take out the constants? So I get v squared over r, the integral of e to the minus 2t rc times 2t. Now, from here I'm gonna go from, remember, no work done to work done. And remember, there's no arbitrary constant for work anyway, right? And this is gonna be from time 0 to a long time. And so we're gonna put up here a very long time. You might go get lunch during that time because it's gonna take a while. Okay? So let's go ahead and take care of this. This is just gonna be w. This is gonna be our same v squared over r. And we gotta figure out what to do here. So the first thing I'm gonna do is remember e to the u du? Remember we had that, e to the u du? So I'm gonna let this equal u. So let's go ahead and do this. So let u equal negative 2t over rc. Then du equals negative 2 over rc times dt. I'm just gonna double check with my third year calc kids here. Dt equals negative rc over 2 times du. I did that right? Luke, am I good? Okay, now I'm gonna substitute this stuff in, and I get w equals all my constants to the outside, v squared over r, negative rc over 2, times the integral from 0 to infinity. And I know that technically in calculus you'd have to change your limits, but we're just gonna do it and come back to the other stuff. Okay, and that's gonna be e to the u du. And we know the integral of e to the u du is just e to the u. So let's do some of this junk in here too. W equals, one of the r's cancel, so we get 1/2 v squared c squared, v squared c. Is that right?
Yeah.
Okay. Times e to the u up. Yeah, we're just gonna go on from 0 to infinity. This right here, what does v equal? Q over c, right?
C.
No, that's not what I want. C equals, yeah, Q over V. So I'll do that later. That's not such a big deal. So W, yeah, so let's, sorry. I'm trying to think, this is only my second time doing this, so I'm still kind of guessing. Let's evaluate this crap right here. So that's gonna have 1/2 V squared, and C is Q over V. So this is gonna be 1/2 QV, which is what we're looking for. But what the hell is this gonna be? Okay? So now that we know what that's equal, I'm just going to substitute that. W equals 1/2 QV, and this is going to be E to the minus 2t over RC, evaluated from 0 to infinity, which is W 1 over QV. E to the infinity, e to the negative infinity is 0. E to the 0 is, oh, we had a negative in here, didn't we? It's right there. Sorry, Murray's an idiot. Which gives us the work done in the resistors is 1/2 QV.
Take a nap.
And that's where, my friends, I get to do this.
That's
Done.
not a lot.